sec. Recording has started. Right, the screen is visible, right? Okay, someone joined. Just a sec.
Yeah, it's visible.
Huh. Okay. Sufficient. So, initially I thought कि पहले वो वाला question I should discuss. Okay, just a sec. I need to get that question here. So, just a sec. Um, huh. So, from file. Right, so this was the question, and it is kind of simple yet not so simple question. So let me just do this. So I hope you guys are able to see. So यहाँ पर basically they have asked कि expectation of y given x1 x2 given x1. What is this a function of? Is this a function of is this a function of just x1 or x2, x1 and x2, or just y? This was the question. D and okay, I hope I am doing this right. I'm not, I mean, I am kind of sure, but थोड़ा सा रहता है ना. Just a sec. Right. So first thing to keep in mind कि let's start off with something really simple कि let's say I have a different scenario. Expectation of y. This is just a number, right? So just a number. So think expectation. What is expectation? Expectation is just an average, right? So whatever this y is, expectation of y is just average of y. So just a number. Expectation of y given x is a random variable, right? So this is not just a number. This is what is the average of y given something. So right. So let's say if I have a classroom where it is divided into two portions, girls and boys, right? So and both of them have marks. So what is the average of marks given girls? What is the average of marks given boys? So this can take two values depending on the value of x. So x denotes gender, right? So if x is girl, then something else will happen. X is boy, something else will happen. So this is a random variable. Now let's go one more step ahead and ask what is expectation of y given x, right? So since this is a random variable, I can take expectations of random variable. Now this can take what values? This can take only two values, right? So it can take expectation of y given boys, and it can take the value expectation of y given girls, and both of it has some probability associated with it. This will happen with the probability that I am choosing a boy, right? So if I multiply this with the probability of boy plus probability of a girl times expectation of y given a girl, this thing will give me my expectation of y given x, right? So this indeed, so these are the two values that my random variable can take, and these are the associated probabilities with it. Now kind of think about it. First of all, we are taking the average of this portion, right? So first we are taking the average of this portion, the girls portion, which is this. Then we are taking the average of the boys portion, which is this. So we took the average of both, and then we are taking the average of these two things. So we'll be left with what? The average of entire thing, right? So there is no point in giving this condition. So ultimately what I'll be left with is the average of marks of the entire class. So this is just expectation of y. So wherever you see expectation of x given y, you can just write this as expectation of x, right? So यहाँ पर expectation of y given x था, यहाँ पर x given y है. So it is just, so the conditioning won't matter. So these are the three very basic rules that you must be aware of. Now let's come to this question. First of all, let's decide ki which is a random variable, which is not a random variable. So here clearly we can see, let's say if we kind of take this to be, let's say something like, let's say k. So then I have what? Expectation of whatever, there is some expression k given x1. So whatever this is a function of x1, right? So I kind of already know ki either this is my correct answer or this is my correct answer. These two are not my correct answers. Then I need to just check ki if x2 is my if this is a function, this entire thing is a function of x2 or not. So let us put things to put names to things. So I have, so what are the possible values that expectation of y given x1 comma x2, this is also a random variable, right? So this the thing which is inside, right? So this is also a random variable. Just a sec, bahar se awaaz aa raha hai, I should just close my door. Just a sec. Right. So let me just, because see, this is the thing that we are taking the expectation of. Okay. So first I am trying to find out कि exactly किस चीज़ का expectation ले रहे हैं हम लोग. So this is what? This is just expectation of marks given my x1 is gender, given my gender and section. Now this thing is a function of both x1 and x2, function of both x1 and x2, but in this expression you have already been given x1, right? So let's say you fix, so we are finding the expectation of whatever this is given x1, so we know that x1 is going to vary, right? So let's just do that. So let's, if we fix x1 to be, let's say male, x1 was gender, right? So if we fix x1 to be male, then what my expression boils down to. So this is basically the key of doing this question. Key, first of all you need to identify ki this entire thing is a function of what. From this very simple fact ki expectation of y given x is a random variable of x, from that I can just say that whatever this is at least a function of x1. So let's just fix x1. Then what is my expression? Expression is expectation of y given male right, because we are replacing x1 with male, x2 given this x1 is male, right. So let's calculate what this is. So what is expectation of y given male comma x2, right. So now this is a function of what? This is again a function of just x2 because I have already fixed my x1 part. So this is basically asking me what is the average of marks for males for both the sections A and B. So again this can take two possible values, expectation of marks given male and section A, which is what? So this is basically average marks of boys in section A, which is given to be. So this is, I hope you guys are able to see, this is the mean marks by gender and section. So the average marks of male given section A is 70. So this thing right here is 70. And what the other thing this can take? This is the probability of y given male and section B. So section B for the male, the average marks is 80. Now we have been asked to take the expectation of this. It can take two values, and now we need to take the expectation of this. Now to find the expectation of y given male comma x2, where x1 is already given to be male, what is going to be this? This is just probability. So इस चीज का होने का probability क्या है? इस चीज का probability is basically कि I am given that it's a male, so probability that I am picking a guy from section A given he is a male times expectation of y given male comma A plus probability that I am taking someone from B given she is a female times expectation of y given, sorry, male, right, because this is also male is fixed, given it's a male and I am taking someone from B, what is the expectation of y given male times B. So what is the probability? This is just number of favorable events by total events. So given it's a male, so I'll just look at the male. So now we need to look at the first table where number of students are given. So what is the probability that I am picking a male from section A? Picking a male from section A is, so total number of males is 50 plus 39, which is 80, which is 89. Total number of males in both section A and B is 89, out of which 39 are from section A. So the probability that I pick a male from section A is just 39 by 80, and this was just 70 plus similarly 50 by 80, and this was just 80. So I evaluated this entire expression for x1 equals to male, right. So whatever this is, so my expectation of y given male, expectation of y given x1 x2 given x1 is equals to whatever this expression is. So what is this? This is 39 times 7 plus 50. What is that? Just a second. 39 times 7 by 8 is 34 plus 80 is 114125. So this is 114.125. How can this be? Nahi, nahi, nahi. 39 times 7 by 8 plus 50 is 84.125. How did I 84.125? Alright, when x1 is male, right, because we had initially assumed that this is a male. Now we do the same thing while assuming that this is female, and we are going to get some number, right. I am not going to do it, it is pretty easy to do it again, and ultimately we will see that this is nothing, just it is just a function of x1, right. So as far as the first question is concerned, it is x1, and now we have been asked to kind of find expectation of this, and when we do, we are going to get this particular thing. There is going to be no one single answer, it because this is a function of x1. So according to x1 you will get two different answers, and this is what you have to write. So this was basically the question. This is, on the surface it is hard. If you kind of know these three basic concepts and you try to do it, you will be able to do it. So that was that. Now let's work on the sufficient statistic part. Right. No, not sufficient statistic, sorry. Sampling distribution. Right. So a very quick overview of what is a sampling distribution. Basically, sampling distribution is the probability. So sampling distribution is the probability distribution of sample statistics. Right, so there is nothing really special going on here. It's just we have studied binomial distribution, we have studied hypergeometric distribution, we have studied lots of distributions. Sampling distribution is just like that. So if I have a function of sample values, say r of x, where x is my sample values, and whatever this is, this follows, let's say, a negative binomial distribution, whatever negative binomial distribution with parameters n, r and p, right. Then my sampling distribution is a negative binomial distribution, right. So sampling distribution is just some different name that we are giving, and so sampling distributions are just any they can be any probability distribution that we have already studied. Now the thing is ki generally when we work with random sampling, basically, so when we are sampling from something, right, when we are sampling from a distribution, we don't know ki what the population of what the distribution of the population is, we don't know. So we kind of make some assumptions, and most often than not we invoke the central limit theorem, right. We invoke the central limit theorem because this is my population, this is my population, I don't know how this population is distributed. This could be binomially. This could be binomial NP. This could be normal mu sigma square. This could be, uh, you know, gamma of alpha beta. This could be anything, right? This could be anything. We don't know what this is. So what do? We take a sample out of it. So this is my sample, and from this sample, let's say we are trying to estimate mu of for population. By the way, if anyone has any doubts, ask me. Shurjo, ask me. Ruby, ask me if you have any doubts. So
Not until now.
okay, nice. So population mu. So if I want to estimate this population parameter mu, I have this sample. I take the sample and I try to estimate it using whatever. So to estimate it, I need some kind of sample statistic, right? I need some kind of sample statistic. I need, to estimate mu, we generally take the sample mean, right? If I want to estimate my population standard deviation sigma square, I can take sample standard deviation. I can take anything. I can take anything, but these are my what MLEs. If you remember, the MLE for mu is x bar. So this is a good thing to take. Now, since we know that we do not know the distribution of population, we do not know the distribution of x bar or sigma square, s square. But invoking the central limit theorem, we can say that okay, fine. I don't know what x bar follows, but I know what x bar minus mu by sigma square by sigma by root n. Why sigma by root n? Because variance of x bar is sigma by root n, right? So that is why we are dividing by sigma by root n. This thing, I don't know what is the distribution of this, and x bar has a distribution. Why does x bar have a distribution?
That will be the standard deviation of x. Variance of x will be sigma square by no.
Oh, right, correct.
Right.
Standard deviation of x. So, and x bar has a distribution. Why does x bar have a distribution? Because we can take another sample here and x bar ka value will change. I can take another sample here, x bar ka value will change. So x bar has a distribution of its own. We don't know what that distribution is. But if we do this, then we know that whatever this is, I'm not talking about x bar anymore, I'm talking about this thing. This will follow a normal distribution with 0, 1. And this is very helpful. Okay, fine, I cannot do so. So I know what the distribution of this is. Now let's say I make an estimate of x bar. Okay, now I want to know ki what is the probability that my x bar is very close to my actual parameter mu. Obviously, this is a very obvious question to ask. Like, what is the probability ki the x bar that I am observing is very close to the actual population parameter? And if let's say the probability turned out to be, let's say 90%, then I am very happy. I am happy that 90%, there is a 90% chance that my x bar is going to be very close to mu. So there is a 90% chance that I am not making a very big mistake. So that is a very natural question to ask. But if I do not know the distribution of x bar, how am I going to answer that question? And that is why we have this. So it's fine, we don't know the distribution of x bar, but we know the distribution of whatever this is, and I can transform my x bar into this, and then we can calculate this probability, because this is a normal distribution. We know normal distribution, PDF, CDF, PDF, CDF, MGF, whatever. So, and then this becomes, so we would say ki the sampling distribution of x bar minus mu by sigma by root n is a normal distribution 0 1. This is what we would say. So this is what a sampling distribution is. Now, since we work and since generally what happens is we do not know the distribution of the sample statistic, and then we invoke. So why is this happening? This is happening by central limit theorem. Okay, so this is happening due to central limit theorem. So what happens is most of the time we don't know the distribution, we invoke the central limit theorem and we get something that is normally distributed. So almost all the sampling distributions are very closely related to the normal distribution. Okay, so this is one sampling distribution that we can observe, which is the normal distribution. What are the other things that we can observe? We can observe a t distribution. So here see, here I am assuming ki so here I am assuming ki I know my sigma, right? But that is again a very unrealistic assumption. I might not know sigma. So sigma is my population standard deviation. If I remove my sigma, or if I replace my sigma, so I don't. So this is when sigma is known. Now let's say I talk about this x bar minus mu by s by root n.
Acha, if we know that our expectation x converges, then by Chebyshev's inequality, can we say that we have a variance, or can we find the variance by Chebyshev's?
Variance of Chebyshev? I guess not, Dada. So by what does Chebyshev say?
Okay.
Chebyshev said that probability that mod of whatever random variable is different from expectation of this is less than epsilon sigma is greater than 1 minus 1 by epsilon square sigma square, I might be wrong here, is this thing, right? Now from here can we find the variance? I guess ভাবতে হবে
I guess it will be 1 minus sigma square by epsilon square.
1 minus sigma square by epsilon square, na?
Sigma square numerator.
Right. এখান থেকে variance for variance what do we need? For variance we need expectation of x minus mu tar whole square. So can we take I guess this is একটু দেখতে হবে, I'll have to see ki
Okay.
Can we find a variance ka bound? I guess not, because if we could have then we would have, but eta Chebyshev diye hoy na, we cannot do it from Chebyshev. That is why we have chi-square distribution, right, for sigma square. So maybe it is not, maybe it is possible, I don't know, you'll have to see. Anyway, so that what I was saying was that okay fine, I don't know my sigma, so what is the natural thing if you don't know your sigma? You replace it with your sample standard deviation. So you compute this, right, where s is your sample standard deviation. Now this won't follow your normal distribution, this will follow some other distribution, and that is your t distribution with n minus 1 degrees of freedom, right? So again, and t and normal are very closely related, right? So if you have, so sampling distribution of x bar minus mu by s by root n is t distribution with n minus 1 degrees of freedom, and these are kind of very closely related, normal. And so let's say this is my normal distribution. This is how, let's say, my standard normal distribution looks like. then normal distribution looks something like this. Wait, basically it becomes bulkier than normal. So they are very similar looking. They are very similar looking, but the T distribution is bulkier than your normal distribution. And why is that? It's because here you know your exact, while talking about normal 0 1, here you know the exact variance of your sample. Here you know the exact the variance of your sample mean. So you have your perfect information about the variance. So that is why the estimate that you are going to make, it is going to be concentrated very close to the actual parameter or actual parameter mu. That is why it is kind of normally shaped. But here you don't have your complete or exact information about your variance. You are estimating it. So your estimates would kind of be thoda sa far off from the true parameter, and that is why it becomes bulkier, right? So these are very related things, very much related things. Now what is next is, so we might be interested in mean, we might be interested in mean when sigma is known, we might be interested in mean when the sigma is unknown. What else might we be interested in? We can be interested in variance itself, right? We want to find the variance, like as Sojo was saying, let's say we want to find the bounds for the variance. How can we do that? So for variance again we don't have, so the sampling distribution of S square is unknown. We don't know this. What we do know is sampling distribution of sigma square of xi minus mu's whole square by sigma square. We know the distribution of this thing, and this thing follows chi square n minus 1 degrees of freedom. Wait, I'll just make sure if what I'm saying is ठीक or not. Where was it? It was somewhere here. Chi square. I guess it was not written here. Dependent random variable. See, yeah, I was right. So this thing follows a chi-square distribution with n minus 1 degrees of freedom. So sampling distribution of not S square, sorry. Sampling distribution of this thing right here, summation of xi minus x bar whole squared by sigma squared is a chi-square distribution with n minus 1 degrees of freedom. And when we say that t n minus 1, chi-square n minus 1, they have actual PDFs, right? So just like normal 0 1 has a PDF, right? So if x follows normal 0 1, that means f of x is some 1 by sigma 2 pi to root 2 pi e to the power minus 1 half x minus mu by sigma whole square, right? So this has an actual, similarly these also have uh, actual PDFs. Okay, so there is a actual, so basically I guess uh, T distribution is just the beta gamma distribution with alpha equals to half and beta equals to half. I'm not sure, I'd have to check. It was either gamma or beta distribution, I forgot. But point being,
Gamma distribution,
gamma distribution.
I
Okay,
think.
nice,
Most probably.
nice. So this is all in the book anyway. So the thing is, they are like not just some abstract things, they are actual distributions. They're just like any other distribution we have studied. So these have expectations to, variance to, they have everything. They have moment generating function, they have everything. Lucky for us, we don't have to go into all of that. It's not that important for us right now. But that is kind of the thing, that these are distributions. This is just some other random variable and this is just some other distribution. That is it. And whatever this is, this follows a chi-square n minus 1. Now I can kind of rewrite this. I can kind of rewrite this to be, I can just multiply 1 by n on numerator and denominator. By sigma square by n, which will just, so what is this? This is just my sample standard deviation, right? So this is just s square by, so n s square by sigma square. This follows a chi-square n minus 1, right? Now let's say that my observed s square is, let's say, 5, and I want to know that what is the probability that it lies between plus minus 1 of the true thing, right? So I'll just kind of convert this into this. I'll just multiply n by 8, I'll this by 8, and now I know the distribution of this. And if I know the distribution of this, I can find the bounds for this, like 1 minus 1, what is going to be this? So this has a PDF, right? So I'll just integrate that PDF, I'll have something here, and I'll get some particular probability. So this is what essentially we will be doing. Okay, so these were the three important thing. Now these are particular examples. So this particular random variable is normally distributed, this particular random variable is t distributed, and this particular thing is chi-square distributed. There is a general formula. What is the general formula? Ki any random let's just write, so let x be any random variable, then x minus expectation of x divided by standard deviation of x will follow let's write it like this. This signifies that this is population standard deviation of x follows normal 0 1, right? X be any random variable, I subtract the expectation of x out of it, and then I divide by the standard deviation of x, which is sample standard deviation. This will be a t distribution with n minus 1 degrees of freedom. And if I have any random variable, I sum it up, square it up, then divide by this. This will be chi-square n. 1. Again, if I take any, let x be any normal okay, so if I take any random variable, let x be any random variable which follows a normal distribution with 0 1, and y be any random variable which follows a chi-square distribution with n minus 1, right. So they can be anything. Then x by root over of the chi-square thing y by the degrees of freedom n minus 1, right. So they don't have to be in this specific form, they can be anything. So if x is any normal 0 1 distribution and y is any chi-square distribution with n minus 1. So whatever this thing is, this will be your t distributed with n minus 1 degrees of freedom. Okay, and let x be any chi-square distributed variable with n minus 1 degrees of freedom, and y be any chi-square distributed variable with m minus 1 degrees, or let's just write nm. X is any chi-square distributed with n degrees of freedom, y is any thing which follows which follows chi-square with m degrees of freedom. Then the ratio of these two things, x by y, will follow an f distribution. So this is again another distribution, an f distribution with degrees of freedom n m m. So which degrees of freedom you write first? The degrees of freedom of the random variable on the numerator. So x has n degrees of freedom, so this will follow f n then m. So these are the basic things. Now we can say something pretty interesting from here, right? We can how are we saying this? This is basically this is coming from here actually. Okay, so we know so we know that this thing x minus mu by sigma follows a normal 0 1 distribution, and this thing right here, what was this? This turned out to be n s square by, okay, this was just sigma or sigma square, this was sigma square, right? This was sigma square. This follows a chi-square distribution with n minus 1 degrees of freedom. So let us just put that into this formula, right? So if I take, so if I in my numerator, if I have my normally distributed thing, so then x minus mu by sigma, right? So this is my normally distributed thing, divided by square root of, what is my chi-square distributed? Chi-square distributed is this thing, so n s square by sigma square, and if I divide that entire thing by n minus 1, then this thing will be what? T distributed with n minus 1 degrees of freedom. Now let's just simplify this. I have x minus mu by sigma. Here I have sigma square under root, right? So that will get out. So I am going to have 1 by sigma under root square under the root n s square by n minus 1, right? So this sigma will cancel out. So this sigma will cancel out, this sigma will cancel out. What else am I left with? I am left with x minus mu by, so there is a root n here, right? Okay, there is a root n here. Okay, let's just take everything out. So I have s square, and then I am left with this n by n minus 1. How do we deal with this? Or am I doing some kind of a mistake?
Yes, হবে.
Huh? Oh, s হবে.
It will be yes.
Right. Nice, thanks. Now how do we deal with this? S by root n, right? Okay, let's just a sec. Let me recheck. I'm doing some kind of kalti. Right? So this follows, ठीक है? Sorry. Oh. So this is right. There is nothing wrong. Now, so this was any x, right? So this was any x with it was any x, the x minus mu by sigma that follows normal distribution, right? Now if I take the specific case, taking the specific case, of xn bar. What is my xn bar? Xn bar is just my sample mean. Then what is my expectation of xn bar? It is just mu. And what is the variance of xn bar? It is sigma square by n. Now if I put it in this formula, then xn bar minus mu by sigma by root n whole divided by square root of what is going to come here? This, right? So right. Here we have the same thing, n s square by sigma square by n minus 1, right? So we are just doing the same thing, but here we were talking about any x, right? So here we were talking about any x that is normally distributed. Here we are talking about x bar. So basically here we would have to here we should have had an extra sigma root n here. So that is what is going to happen. Again the sigma is going to cancel out. Sigma is going to cancel out again. Okay, we are going to have 1 by root n, which is going to go up, and I am going to have a sigma here, and this sigma will come out. So I am going to have a 1 by sigma here too, and what else is going to be left? I should have s times n by n minus 1, right? This sigma cancels out. I have square root of n x bar minus mu by s of n by n minus 1, but I don't think there was a n left. What happened? To see why, u can be written as this. Oh, okay. Right. So what they have basically said is that now if as n gets larger and larger, right, this thing right here this thing right here goes to 1. Okay, and so ultimately as n gets larger and larger, what we are left with, so limit n goes to very big, whatever this expression is, this becomes essentially this. And you can rewrite this as x minus mu by s by root n, and this we know follows a t distribution. Why? Because this thing right here, this followed a t distribution, right? Because we just put this and this in the formula for what the p distribution would t distribution would be, this formula. So we know that this follows a t distribution. So these was some of the things. Now let's just look at a few questions from 8.1 to 3, hopefully 4 and 5. So 8.1 isn't too big, it's a chota sa thing. Can I? No. How do I? Anyway, so where is 8.1? Right, so they have just said what is a statistic, what is an estimator. Statistic is any function of the sample values. Estimator is again any function of the sample values which we use to estimate things. So there is no real difference. Okay, and every statistic has a sampling distribution. They have kind of given an example here. This is the actual definition of a sampling distribution. Purpose I just told you, right, ki they are estimating some theta hat and they want to know ki what is the probability that theta hat and the difference between the true theta and the theta hat, that is something that we are estimating. What is the probability that that difference is less than some value? We want to know that, let's say. So to do that we need the sampling distribution. Few examples, and it is basically it. Now if we kind of look at the question, right, so for let's say look at the first question. Suppose that a random sample x1 and xn is to be taken from the uniform distribution with this thing, theta is unknown. How large the samples must be in order to make this probability less than this, right? So let yn to be this thing so that it will make our lives easier. Okay, so what do we need to find? We need to find the probability. I mean, we need to find a sample size. We need to find a sample size such that this yn minus theta is less than 0.1 theta. That is the estimate that I am making, and the true parameter. So that is not 10% away from the true parameter. It should be within 10% of the true parameter. That probability is greater than 95%. Now I can kind of remove this mod as follows, right? I can remove this mod as theta minus 0.1 theta is less than or equals to yn is less than or equals to theta plus 0.1 of theta, right? I can do that, and that is basically probability that my yn lies between 0.9 theta and 1.1 theta. Now we need to kind of do some I mean kind of notice something. what is yn? Yn is maximum of these sample values, right? That is what my yn is. Now this was taken from a distribution which is 0 theta, right? So basically I have a distribution like this. My true distribution is 0 to theta, and then I am taking some values. So some values might lie here, some values might lie here, here, whatever this is. Theta is my true parameter theta, and we say that, okay, what is the maximum value of x? Let's say this was the maximum value of x. So this becomes our theta hat. This is what we are saying, because we don't know what my true theta is. Now can this theta hat ever lie out beyond theta? Can this theta hat lie here? No, right? Because if my true population is from 0 theta, there is no way I can find a value, sample value, which is beyond theta. I am saying ki, okay, so let's say I know the true distribution. Okay, I know ki I will be drawing values from randomly distributed 0 to 10, and let's say you don't know what the distribution is. So you ask me, give me one value. I give you, let's say 0. You say, okay, give me another value. So I am picking values from this distribution only. I say, okay, I'll give you 9. I'll give you, then again you ask me 8. Again you ask me 7. Again you ask me, I gave 2. I give you multiple values, because I am multiple values from this distribution. I know this distribution, you don't know this distribution. Now based on these values, you are asked to kind of guess ki what my distribution is. You are going to say, okay, since the maximum value is 9, I am guessing that you are giving me values from uniform 0 to 9, right? So this is the best that you can do. Now will you ever make, so given the fact that you have seen these particular sample values, will you ever make a guess of 0, 11? Why will you make this guess? You will never make this guess. You seeing the maximum is 9, so I'll give 9, right? And so that is one thing. The other thing is, given that my true distribution is 0, 10, will I ever give a value of, let's say, 12? Can never happen, right? Because I am picking values from 0, 10.
No.
Yes, no. So that is exactly what is happening here. These are all my sample values, and I am taking the maximum of the sample values. Now the maximum sample values, can that lie beyond my true parameter theta? No, it will always lie, it will always be less than. So my theta hat is always less than or equals to theta, which implies my theta hat is always less than or equals to 0 plus 1 theta plus theta, which implies theta hat is always less than or equals to 1.1 of theta. Always, with probability 1. So probability of this happening is 1. You will never go beyond theta, let alone 1.1 of theta. So we don't need to worry about this. This is always 1. Yn will always be less than 1.1 of theta. All we need to take care of is this thing, ki what is the probability that y 0.9 of theta is less than or equals to yn, and this probability needs to be greater than 0.95, and I can just write that as probability yn is greater than or equals to 0.9 theta, where again I can write yn to be less than or equals to 0.9 theta. I am taking the complement, so this will become less than or equals to 0.05, 1 minus, right? I am doing 1 minus, okay, so this becomes, will this be greater than or less than? what am I doing? I am looking at the probability that yn is greater than 0.9 theta, and that probability should be 0.9. So 1 minus probability of yn being less than or equals to 0.9 theta, that should be greater than 0.95. This implies 0.05 should be less than or equals to probability yn is less than this, right? So probability of whatever this is should be greater than, right? 5 is less. So this thing. Now I know what this is. See, because what is yn is maximum of x1, x2, xn, right? So yn is the maximum value where each xi follows a uniform 0 theta, right? Now if I say that yn is less than or equals to some value, let's say yn is less than or equals to some value k, what does that imply? X1 was less than or equals to k, x2 is less than or equals to k, so on, xn is less than or equals to k, right? Because if any one of this is more than k, then yn would have become k, or yn would have become that value. So basically I am saying कि अगर yn का value 5 है, that means what? Whatever sample that I have observed, all the values should be less than 5 or equals to 5 if y is my maximum value, right? So what is the probability that yn is less than or equals to k? The probability that yn is less than or equals to k is probability that each one of these values is less than or equals to k. Now this is a random sample. If this is a random sample, then I can just multiply this probability. This is my joint probability, and since this is a random sample, they are independent of each other. So this is just probability that x1 is less than or equals to k times probability x2 is less than or equals to k, so on till probability xn is less than or equals to k. Now x1 is what? It is an uniformly distributed variable. So f of x1 we know it is the value k minus the lower limit by upper limit minus lower limit. This is, so if you do not know this formula, go back to uniform distribution, you will find this. Here the lower limit is 0, upper limit is theta. So in this case it is just k by theta, right? So we have k by theta n times. So it is just k by theta to the power n, because this is going to be k by theta, this is going to be k by theta, this is going to be k by theta. All of them multiply it, you will get k by n, k by theta to the power n. So what is the probability that yn is less than or equals to 0.9 of theta? Replace k by 0.9, 0.9 theta by theta to the power n, which is just 0.9 to the power n. Now they have asked ki, so this left hand side turned out to be 0.9 to the power n. What is the value of n such that this is greater than or equals to 0.95? I don't think this should be greater than, right? This should be less than. I am kind of going wrong somewhere. This should be less than. This should be less than, right? Making some kind of a mistake. Because this probability greater than 0.95 doesn't make sense. I'm basically, I started off with the thing ki what is the probability that it would be within 10% of my true parameter should be very high, and now I am looking at the, so that should mean that the probability that my estimate is beyond 10% of my, beyond 10% of my true parameter should be very low, right? So this probability should be very low. Precisely, this should be lower than 0.95. This should be less than. So now I need to find the value of n such that this thing is 0.95. There are multiple ways of doing it. Easiest way is to just take the log. If you take the log, you will get n log 0.95 is less than equals to log of 0.95, which is equals to, which implies n should be less than or equals to log of 0.95 by, sorry, this was just 0.9, log of 0.9. You will get this value, you will get something. Let's say you got 2.36, you just make it 3 or whatever, because n should be an integer, right? N cannot be a decimal number. And you round up, you don't round down, you round up, because if the n is bigger than what you need, it's okay. It cannot be smaller than what you need. So you round up and you will get a value. So where is the sampling distribution part in this? यहाँ पर sampling distribution कहाँ लगा? Sampling distribution was exactly this part, right? Ki I know what the sampling distribution of yn is, right? I know because I knew what the sampling distribution of yn is, I was able to come up with this expression. If I did not know this, I wouldn't have been able to come up with this expression, and I wouldn't have been able to calculate this probability, and I wouldn't have been able to find my sample size. So that is the sampling distribution part. That is how sampling distribution comes into the play. So, and more or less all these questions are of the same flavor. They are not exactly the same. This was very, I mean, we did not have to apply t or chi-square or anything. In different questions we need to, I guess, I haven't done every one of them. So for instance, this is even easier. Ki what is the expectation, ki what should be the sample size, so that expectation of this thing x n bar minus theta ka squared is less than or equals to 0.1. Just a sec. Just a sec. Okay. So here they have asked you what is the expectation of this should be less than or equals to 0.1. Now what is this expectation of this? It is just variance of x bar, right? It is just variance of x bar. Because what is variance of x bar? Variance of x bar is, I mean, what is variance of any variable x? It is expectation of x minus expectation of x ka squared, right? So what is going to be the variance of x bar? Variance of x bar is expectation of x bar minus expectation of x bar ka squared, which is just expectation of x bar minus mu ka squared, right? Here they have taken mu, I have taken mu, they have taken theta, unknown mean theta. Theta is the unknown mean, population mean. So this is just the variance of x bar, and that should be less than or equals to 0.1. Now what is variance of x bar? X bar we know it is sigma square by n. It should be less than or equals to 0.1. So my n should be what? Bigger than sigma square by 0.1. That's it. The sum is done. So well, this is it. And what I would kind of suggest is try a few of these examples, few of these questions, and look at the solution for all of them. I mean, if you do not have the time to solve each and every one of them, fine, but at least see ki baki sab the other questions how they have solved it, because there is only 9, right? So do as much as you can and look at how they have done these things, right? So for instance, I'll just do one more, which I think is different, which is 5 5. They have said ki suppose that a random variable is to be taken from a Bernoulli distribution with parameter p. Suppose that it is believed that p is in the neighborhood of 0.2. So how large the random sample must be in order that this inequality holds. Now, what is xn bar? Xn bar, so I have a Bernoulli distribution, right? So I have a bunch of zeros and ones, and xn bar is sum over all the ones divided by all of the n's, right? Xn bar was just the proportion of ones, if you remember. So that is what xn bar is. What is going to be n xn bar? Or we cannot, let's do it some different way. So xn bar is my that mean, sample mean, and p is my population mean, right? Population, that is the population proportion. So if I, so this is my mean, this is my population mean. If I divide this by the standard deviation of x bar, right? If I divide this by standard deviation of x bar, then I have a standard normal distribution. So x bar minus p by what is variance of x bar? Variance of x bar is sigma square by n. Sigma square is population variance is npq, right? npq, binomial distribution. Don't remember the formulas, go back, you will find these formulas, no issues. So what is my variance of x bar? npq by n, which is just pq, right? So if I divide this by pq, q is what? 1 minus p. Then this follows a normal 0 1. They have said that p is 0.2, so just put the value of p here. So if p is 0.2, so I have x bar minus 0.2 divided by 0.16 to 0.2.0.8, 0.16. So I have this. So I have this. I don't have this. So what I will do? So basically I have probability xn bar minus 0.2 is less than or equals to 0.1. What is this what is the sample size so that this thing is greater than or equals to 0.75? Now, why did I replace p by 0.2? Because it is given कि p is 0.2. Now I don't know what the distribution of this thing is. I know distribution of this thing. So what I need to do to get यहाँ से यहाँ जाने के लिए, I'll just divide by 0.16 on both sides. So if I divide this, so I'll get xn bar minus 0.2 by 0.16. This should be less than or equals to 0.1 by 0.16. It should be greater than or equals to 0.75. This is just some standard normal z mod z being less than 0.1 by 0.16, and that is greater than or equals to 0.75. I know this distribution, right? So this looks something like this. This is my standard normal distribution, and mod of that should be less than 0. Wait, did someone join?
আরে পার্সেল এসেছিল বেরিয়ে গেছিলাম, মনে করিস না।
Oh. So this is just the probability that z lies in this region, right? So this is my 0.1 by 0.16, this is minus 0.1 by 0.16. So what is the probability that z lies between this? So this is exactly equals to 1 minus the probability that z will lie in this yellow region. So this is so what is the probability that z would lie in this yellow region? It is just phi of minus 0.1 by 0.16. Now what is the probability that z will lie in this region or this region? Now by the symmetry we know that this region, the area of this thing is equals to the area of this thing. So the probability that it will lie in either one of these two region is just 2 times this, and the probability that it will not lie in this yellow region is just 1 minus this thing, right? So ultimately what do I have? I have, putting everything here, the 1 minus 2 phi of this should be greater than or equals to 0.75. Iska value would be given from the table or whatever, and we'll be able to find out n. Right. This should be, यहाँ पर एक n होना चाहिए था. तो variance is sigma square by n. Standard deviation is, okay, just a sec. This is 8.4. I'm doing something wrong. What am I doing wrong? Right, variance of xn bar is 0.16 by n. Why is this true? Variance is, variance of xn bar is not npq, it is just pq, because xn bar is not binomial. Oh fuck, sorry, so I just made a mistake here. This shouldn't have been npq by n, it should be just np by n. So here we would have pq by n, so pq by n, and this is with 0.16 by n, and so we would have to divide by, so point being कि यहाँ पर एक n होता, and this would have been a function of n, right? And from here we will just we'll isolate this thing, this would be greater than some particular value, right? So we can take minus 1 there, 0.25 aega, we'll divide it by 2, we'll get something, and then we'll just look at the value of, let's say यहाँ पर 0.66 आया, so we'll just look at the table of values for the CDF and see for what value the area under the curve is 0.66, and we'll equate that particular value with whatever is inside here, and then we'll solve for n and we'll get the value of n. I know this is a bit confusing, but once you start solving these things, you'll get the hang of it. 8.2 is chi-square distribution. There is nothing really special going on here. You just need, so I would say completely ignore the theorems right now. Just remember the properties, and that should be it. I don't think we are going to get questions directly from these distributions, because ma'am has not spent too much time on it. Ma'am spent much of her time in 8.4 and 8.3. So those are the two like important areas. But as I was saying, chi-square distribution is just a distribution, so it will have an expectation, it will have a variance. No need to derive this, you just keep it in mind. Also no need to keep it in mind, this will be in the cheat sheet. I hope so. And if you have, let's say, k random variables, k chi-square random variables, and if you add them up, you are going to get a random variable, chi-square random variable, but the degrees of freedom you need to add them up. And that is basically it. Now basically the kind of question that you might get from here is like this, है ना, कि what is, this is some statistic t, what is the probability that t is less than some c is 0.9. So here you need to kind of identify J, t is essentially a chi-square distribution with 20 degrees of freedom, sorry 19 degrees of freedom, n minus 1, n minus 1. So what is the probability that some chi-square variable is less than or equals to c is equals to 0.9. This particular value of c you will get in the table of you will get in the table of CDF of chi-square, and that is where your sum ends. And more or less this is what you have to do in almost all of these questions, right? So they are, for here they have asked us to show that this follows chi-square distribution. This is something that is done by Rohini ma'am, this entire thing, or whatever we did here, right? That is precisely what we did. We showed that this follows a chi-square distribution. No, we did not show this. We showed the t distribution wala portion. We did not show this. Okay, we did not show this, but this can again be shown. Obviously, I am sorry I cannot discuss a lot of questions right now, but this is pretty much all that there is, and I guess we should focus more on 8.3 and 8.4, not on 8.1 and 8.2. 8.3 also, a lot of the questions are just not there because it involves matrices. Now matrices, although we know, since this is not something that Rohini ma'am has done in our class, I guess question number 6 and question number 7 should be enough. I mean, these two questions everyone should try. I haven't tried it myself because I did not have the time. I'll try it today, and maybe we can discuss this the next time. And 8.4 is just t distribution. So majority of the question would just be identifying some particular test statistic t follows what distribution. Just like in normal we used to do, I have been giving some random variable, we convert this to a z distribution and then we find the probability. Same thing, we will be given some statistic, we need to convert it into either chi-square or t or z, and then we need to find the probability. There is nothing else that we are doing. Confidence interval, let us discuss sometime else. I don't think we have much more time here, it's already 2. So any doubts?
No sir.
Okay then. साहिल बोला या सूर्य बोला, कौन बोला?
नहीं, मेरी तरफ से बोल दिया शायद.
ओके, कोई डाउट वगैरह होगा भेज देना. I'll look into it, we'll discuss it together and then we'll be able to do it. Okay then, ending the call, right?
Oh, okay.
Sure.
Bye, tada.